Okay, this is section 4.4. We have been learning how to do confidence intervals. Now we're just going to learn about them a little bit deeper. We're going to learn about factors that affect the width of the confidence interval and also talk again about what the confidence level means. So to start with, let's just review our confidence intervals. So we know all confidence intervals have this form where it's the statistic plus or minus some margin of error. And that margin of error is a multiplier times the standard deviation of that statistic. So for proportions, if you want to know the population proportion pi, then you'll do p hat plus or minus z star, that's your multiplier, but the applet does all of that for us, times the square root of the p hat times 1 minus p hat over n. Okay, that multiplier, the z star, is just 2 for 95% confidence. That's the only one we have memorized. Everything else, we just use the applet. And it's valid with at least 10 successes and 10 failures in each sample. Otherwise, these multipliers that we're calculating just don't work. For our population mean mu, then our sample mean will be our sample mean plus or minus a t star, because we have to use the t distribution for means when we estimate our population standard deviation, times s, the sample standard deviation, over the square root of n. Again, t star is about 2 if you have 95% confidence. It's valid with a normal population or a large sample size. Now, because it's a t distribution and it has more area in the tails, it will work if your sample size is at least 20 and at least like almost symmetric. That's the rule that the book has. Really, once you get to sample size of 30, it will work for any shape of data. A note here, confidence intervals are only as good as your sample. So if you have a bad sample, you're not going to get an accurate confidence interval, even if you do the math correctly. So you do need to remember you need a random sample from your population that you're interested in. You want to avoid voluntary responses or convenient samples, like you don't want people volunteering to be in your sample. And you need to avoid a bad sampling frame. So remember, the sampling frame is the list that you choose your sample from. So if I want to find the age of everyone at USU, but I only ask freshmen instead of asking like a sample from everyone at USU, I'm going to get a very bad answer, very inaccurate answer, because I'm only talking to freshmen. I have that smaller sampling frame. Okay. Also, you want to avoid non-sampling errors. Remember, things like people can change their minds, or they don't remember correctly, they lie, or there's social expectations. Sometimes there's leading questions or confusing questions, or just the interviewer can kind of sway them one way or the other based on their attitude or their responses. You also have non-response, which is when you select people to be in your survey and they refuse to participate. So just kind of a quick review helps you remember the things we've learned throughout the class, and when we get to the final, you remember everything when we kind of review it as we go. Okay, so let's talk a little bit about understanding confidence intervals and what those actually mean. So what we're going to do is we're going to look at the Gettysburg Addresses and the eyesight applets under randomness and sampling words. So if you're familiar with the Gettysburg Address from Abraham Lincoln, it's fairly short. It's about 268 words. Which works really well for us because then we can actually look at everything in the entire population. So in this case, the population is all the words in the Gettysburg Address. So when I pull it up, you have Gettysburg. You can see all of the actual words, like so 7 years ago, our fathers brought. Okay. And it will tell you a lot of different information about it. But so this is our entire population. So looking at this, let me show you on the applet. Okay. When I click use data, or even if I don't, because it's just the default one that comes up, you can see this is the population data that it will show you here. So this is a population, okay, because it's all the words, not just a sample. It was a very short address, so we actually have every word. When we look at it, it will tell me the mean, and we want to use the correct symbol, so we'll do it as a population mean, so it's 4.295. What is the standard deviation and its symbol? This is, again, the population standard deviation of 2.119. And what is the shape? Well, it's not normal. In fact, I say it kind of has that long right tail, so I would say it is skewed to the right. It has a long right tail. Let's see, what is the variable in classify? Again, this is kind of just reviewing things that we did earlier in the class because we want to always keep everything fresh in your mind. So the variable we are looking at, I don't think I told you. Okay. Coming back, there's different variables you can choose. So you can do the length of the words. You can do short. It's just like, is the word short? Yes or no. Does it have the letter E? Yes or no. Is it a noun? Yes or no. So just different variables are put in there. But the variable we're looking at right here is the length. So the variable is the length of the word. And if you think about length of the word, well, I guess you could think about it different ways. So if you look at the data set, the length, these are numbers. It's actually counting every letter in the word. So those are numbers. So that is going to be quantitative. It did also have the option of just short yes or no. That would be categorical. But the length that we're looking at is actual numbers. So actual numbers means this one is quantitative. What are the units? Okay, this is kind of a tricky question. If you're just looking at the length of the word and you're just counting letters, your units would be letters. So 5 letters, 6 letters. If we are to take a random sample of words, what size of sample is needed to be able to do any theory-based approaches, whether it's tests or confidence intervals? Because we want to take a random sample, if we look at our data is skewed. And if our data is skewed, then we need a sample size of at least 30. If our data wasn't skewed, then 20 would have worked just fine. And if our data had been normal, then any sample size would have worked. But since it's skewed, we do need a sample size of at least 30 to use any theory-based approaches. So I'm going to take one sample of size 30. To do that, I come to my applet and I click Show Sampling Options. You can ignore the stratifying clusters. That's just making sense. I want one sample. I want a sample size of 30. And I click Draw Samples. And it will show you the actual words that it drew in this random sample. So the words were like, so, what, testing. And you can see the lengths of the words like 2, 4, 1, 7. I think that's a little bit bigger. You can see that this is my most recent sample. This is a sample I just took. These are the actual, each blue dot represents an actual word, like one word. Okay. And then this is my one sample mean. So it's your sample statistics. I got a mean of 4.233. So here's the dot right here for 4.233. Okay. And then let's come back to our notes. So this one was different than the one I just showed you because it's a different sample. So in this one, from this sample, I got a sample mean of 4.4 and a sample standard deviation of 2.027. So let's take these values and come put them up here. So my sample mean in a symbol is we got a sample mean x bar equals 4.4 and a sample standard deviation of 2.027. So let's find a 95% confidence interval for the population mean using the 2SC method. So we know it's x bar plus or minus 2 times our sample standard deviation over the square root of n. So my sample mean is 4.4 plus or minus 2 times my standard deviation of 2.027 over the square root of n, square root of 30. So this is 4.4 plus or minus. So sometimes you can do the 2 times 2.027 divided by the square root of 30 and do your whole margin of error. Some people like to write it like that. So it's 4.4 plus or minus 0.74. Then I can put that in my calculator. So if you find that easier, you are welcome to do that. So we have 3.66 to 5.14. So if I was to look at this, just to review, my center is 4.4. And my margin of error is the 0.74, so part of the add and subtract. Okay, so that's really just review. So that would be my confidence interval based on that sample. Okay. Notice again, this is my actual sample here, and I kind of changed the way it all looked just so it fit on the page. Okay. These are my sample statistics, so this is my one sample mean so far. Because I've only taken one sample. Now I could come back and I could take another sample. Notice now my data looks different. I have a different mean and a different SD. And now I have a different mean that just showed up on my sample means block. So now I have 2 sample means that I've done so far. Okay. So here's another sample of size 30. Find the 95% confidence interval. So this is my sample. And so I would do x bar plus or minus 2 times s over the square root of n. So my sample mean is 4.2 plus or minus 2 times the 2.156 over the square root of 30. You can put in your calculator in 1 step or 2 steps. I'll just do 1 step now. Hopefully I put it all in. No one's here to correct me. 3.41 to 4.99. So that's my confidence interval. Now, do you notice, is there a difference in these confidence intervals? So before I was at 3.66, now I'm at 3.41 as my lower endpoints. Okay, and my upper endpoints looks like they changed as well. So every different sample I pick gives me different confidence intervals. So now I've taken 2 samples, so here's like 2 sample means. Okay. Different sample means give us different confidence intervals. In fact, let's write that out, that different samples give us different confidence intervals. So I went through while I made these notes and took 10 total samples of size 30. So here are my different samples. Here are their sample means. Here's their standard deviations. And I even found different confidence intervals. So now what I want to know is how many of these confidence intervals contain the population mean mu, which was this 4.295, because we actually have all the population. We can actually calculate that. So as I go through 4.2, yeah, that's between 3.66 and 5.14, so that'd be yes. 4.2, yes. Yes, yes. So I go through, I think all of these contain 4.2, yes, yes, yes. Oh, not this one though. So those are all yeses. When I get here though, 4.2, that's above 3.95. So this one does not contain my population parameter. Let's see, yes. Oh, this one doesn't either. Like 4.4 is above that. So this one is also a no. Okay. So most of those contain my population parameter, but 2 of them didn't. So there were only 8 out of 10, or 80% of our intervals that contained the population parameter. But that's only 10 samples. 10 samples is still pretty random. So I asked the computer to take 100 samples of size 30. So this is a different applet. We used this one previously though. So back to your eyesight applets, we want exploring randomness, simulating confidence intervals. We are now dealing with means. We know our population mean is 4.295, I think something like that. The population standard deviation is 2.119. And we can put in our sample size of 30. And I can ask for 100 intervals instead of just 10 intervals. So now when I sample, look, this time when I did 100 intervals, there were 4 confidence intervals that did not contain my population parameter. Those ones show up as red. So about 96% did contain my population parameter. If I take a different set of 100 samples, well, this time it was 93% that contained my population parameter. If I take another set of 100, oh, this time I had exactly 95% that contained my population parameter. You'll notice when you look at it that it will tell you your most recent sample. It will also tell you your sample statistics, your midpoints. And so my sample means, I had most of my sample means were in the middle, and then they're green. That means their confidence interval contained the population parameter. The red ones are ones that didn't contain it. You'll also notice the confidence interval widths. The widths change. The reason the widths change is because every sample has a different sample standard deviation. That's what you can see right here, like different samples have different standard deviations, so the confidence intervals are different widths. Let's see. So for the set that I put on here, what proportion contained the true population mean mu of 4.295? It looks like 93%. So at 100%, or at 100 intervals, we're getting a little more predictable. I can tell you there were 93% from that set of 100. But I could find more sets of 100. So here's different sets of 100 confidence intervals. The first one had 95% that contained mu. The next one had 96%. The next one had 98%. But somewhere around like 95% of our confidence intervals are actually containing our population mean mu. Of course, we know from simulations that 100 is still a pretty small number of repetitions to run any simulation. So let's try asking for 10,000 confidence intervals. So I asked for 10,000, and this is what it looks like. It's actually showing me 10,000 different intervals, even though it just looks spiky. This time, exactly 95% of my confidence intervals actually contained the population mean mu. And we could try that here to see. So I asked for 10,000 intervals. Notice this time it's at 94.8%. But if I keep trying, I'm just going to get closer and closer to exactly 95%. So now out of my over 20,000, I'm exactly at 95%. And as I keep going, if I just get more and more samples, I'll just hover right there around 95% of my confidence intervals that are actually accurate. So the reason we look at all that is it helps us understand confidence levels. Okay. So we're going to call the intervals we made 95% confidence intervals. 95% confidence means 95% of the time the interval we make will capture or contain or cover the population average. Unfortunately, that does mean 5% of the time the confidence interval will not contain the true population average. Or you can think about it of a 95% confidence level means if we took thousands of samples and found confidence intervals for each sample, then about 95% of those confidence intervals actually contain the true parameter. And we talked about this before, but let's just go over it again. So to interpret our confidence interval, our official interpretation, you can think about it a couple ways, is like we can be 95% confident that the interval we've constructed contains the true average word length for the Gettysburg Address. The correct answer will always talk about the true population average. You can also think about it as 95% of the possible confidence intervals would contain the true average word length. So some bad interpretations, 95% does not mean that 95% of my data is in the interval. Okay. So I took one sample and got the words like what, cuz, the, but, etc. So there's my actual words in my sample. So the sample average is 3.9. Okay, and my confidence interval is 2.92 to 4.88. So if you look at the individual word lengths, do you think 95% of the lengths are between about like 3 to 4 letters? Are they in that range? Well, that was 4, but that's 5. Let's see, 3 through 3, 3, 4. That one's like 6 or 7. That's a 2-letter word. That's a 5-letter word. That's a 6-letter word, a long word, 5 letters, 2 letters, 2 letters, 5 or 6 letters, 6 letters. There's a lot of words up there that had lengths that were outside this range of 2.9 to 4.88. Okay, so individual values don't have to fall in our confidence interval. In fact, if you think about it, remember if we have our population, like if this is my population, then my sampling distribution is always skinnier. My sampling distribution of possible sample means is always skinnier than our population. Okay? So our confidence interval is always skinnier than our actual population of individual values. So you should never pick the answer that talks about individual values. Also, let's see, 95% does not mean that 95% of the other sample averages are in our interval. Okay. It seems like it should be accurate, but it's not, because we do know that 95% of sample averages will be between our population average plus or minus 2 standard deviations. But my confidence interval is based on a sample average plus or minus 2 standard deviations. And so those two numbers or intervals do not line up. So you should never pick the answer that talks about sample averages. Let's look at changing the confidence level. We've talked about this one a few times already. So I took one sample, this is still the Gettysburg Address still, and I got sample mean of 4.133, standard deviation 2.161, sample size is 30. Using the theory-based inference applet, I found these confidence intervals. So here's my 90%, 95%, 99%. And I graphed them to scale, and you can see as my confidence interval gets higher, my interval has to get wider. And I also simulated these for you so you can actually see what it looks like. So notice at 9%, they're pretty skinny. 95%, they're getting wider. And 99%, they're getting wider yet. So again, the only way to be more confident is to make your confidence interval wider. So as the confidence level increases, the confidence interval has to get wider. Now, on the tests and homework and things, she might ask you, like, what happens if you switch from 95% to 99%? Or what happens if you go backwards, like from 95% to 90%? So every time, just draw out something like this for you, and then just kind of use logic to figure out, am I going down? Am I going up? Just draw something like that, and then figure out the answer to the question. Okay, what happens if we change the sample size? So remember, the sampling distribution for possible sample means has a standard deviation of x bar equals sigma over square root of n. So if we increase the sample size, the sample-to-sample variability, this standard deviation of x bar, should decrease, because if n gets bigger, if you're dividing by something that's bigger and bigger, then your entire thing, mathematically, if you divide by a bigger number, then overall it gets smaller. Okay. So here are some simulated possible sample means from the Gettysburg Address. So you can see it says sample statistics. So these are all of my different sample means. So for sample size of 30, 100, and 1,000. And it's actually 2 scales, so you can see it gets skinnier and skinnier for a bigger sample size. So bigger sample sizes mean smaller standard deviation of the possible sample means. Well, then if you think about it, for a smaller standard deviation of the possible sample means, our confidence intervals should get narrower. Because if you think about it, if you're going to pick in here and pick, like, make a confidence interval, your confidence interval is a lot smaller here at 1,000 than it is for 100. The hint to figure this out is, well, our 95% confidence interval is x bar plus or minus 2 times s or square root of n. If this gets bigger, then this entire thing has to get smaller. Okay, so for smaller standard deviation, that means our confidence intervals are going to get narrower. Okay. Just so you can see that in action, I took a sample and got these statistics. Using the theory-based applet, I found the confidence intervals for different sample sizes. So here's my standard error. So for sample size, let's write sample size here. So for sample size of 30, my standard error is 0.395. For 100, my standard error is 0.216. And for 1,000, my standard error is 0.068. Notice my standard error is getting drastically smaller. And so here's my different confidence intervals. And you can see at 1,000, it is much skinnier. And so then I drew out the confidence intervals for you to scale, and you can see at 30 or 100 or 1,000, as we go up in our sample size, my confidence interval gets narrower and narrower. Okay, I'll just cross that off. Sorry, that was left in there from before. So as our sample size increases, the confidence interval will get narrower or skinnier, okay, because bigger sample sizes let us be more precise. Now, as a remark, we just looked at that for sample means, but we can do the same thing for proportions. If we're using proportions for categorical data, then the sampling distribution for the possible sample proportions has a standard error where it's p hat times 1 minus p hat over the n, and then you take the square root of everything. But if n's getting bigger, then this entire thing's going to get smaller. So bigger sample sizes mean smaller sampling variability overall. So bigger sample sizes still mean narrower confidence intervals, whether you're doing proportions or means, it doesn't matter. Okay. Well, what happens if we change the standard deviation? So if we have a quantitative variable, numerical data, we summarize it with the sample mean and standard deviation. And our 95% confidence interval is this x bar plus or minus 2 times s over square root of n. What would happen if we increase the standard deviation s? So just using logic, if we make s bigger, if s gets bigger, then this entire thing is going to get bigger because we're just multiplying by a bigger number. So our confidence interval should be wider. So if you increase the standard deviation, then our confidence interval is going to get wider because that whole margin of error is bigger. So that you can actually see it, I took a sample. Here's I got sample mean 4.1, sample size is 100. What if we keep everything else the same and change the size of the standard deviation? So using the theory-based applet, I found confidence intervals for these different standard deviations. So when s is 2, my standard error is 0.2. When s is 3, my standard error is 0.3. And when s is 4, my standard error is 0.4. And if you look at the confidence intervals, I seem to be getting wider and wider and wider. So if we increase our standard deviation, the confidence interval gets wider. So as the standard deviation of your data increases, the confidence interval gets wider. Now, you don't necessarily have to memorize all of these, because on the test, if they give you the data, you can just put the data into the applet, find the confidence interval, and see which one is wider. Okay, but it does help if you can understand this, and if you can memorize it, great. But if you forget on the test, just put everything in the applet, find the actual intervals, see which one is wider. Okay, well, what happens if we change the sample proportion? So if we have categorical variables, we summarize it with our sample proportion. So let's suppose we want to look at the sampling distribution of possible sample proportions for various levels of pi, our population proportion. What values of pi give us the highest sample-to-sample variability, the standard deviation of pi? So if pi equals 0.1, my standard deviation of my possible sample proportions is 0.03. When pi equals 0.3, my standard deviation is 0.045. When pi equals 0.5, my standard deviation is 0.051. For pi equals 0.7, we're at 0.044, and pi equals 9, we're at 0.048. So you can see the biggest standard deviation is here at a population proportion of 0.5. So pi equals 0.5 gives us the biggest standard deviation of p hat. So values of pi close to 0.5 give us bigger values of our standard deviation of p hat, and values of pi farther away from 0.5, the farther you get smaller values of our standard deviation. So with that in mind, with our standard deviation, if our 95% confidence interval is this p hat plus or minus 2 times all of that, or just p hat plus or minus 2 times the standard deviation of p hat, okay, what's going to happen to our confidence interval? If p hat is farther away from 0.5, that means we have a smaller standard deviation of p hat. And if we have a smaller standard deviation of p hat, then that's going to mean a narrower confidence interval. So let's actually try it out with some numbers. Suppose we want to take a sample of size 100, find a 95% confidence interval for the population proportion. Let's look at what we actually get for different values of p hat. So for p hat of 0.1, my standard error is 0.03. For 0.3, my standard error is 0.044, etc. So the widest confidence interval will be when p hat is, okay, let's see, where's my biggest standard error? My biggest standard error is 0.05. So that's going to happen when p hat is 0.5. And the narrowest interval will be when we're at 0.1 or 0.9. Okay. So the closer you are to 0.5, you get wider intervals. The farther you go out in the tails, you get narrower confidence intervals. Okay, so as your sample proportion gets farther from 0.5, the standard error decreases and the confidence interval gets narrower. Again, this one would be really weird to try and, it's like one more thing to memorize. You can just put your confidence intervals into the applet, find the confidence intervals, and answer the question. Okay, so one more thing. This one actually goes back to significance tests. We're going to kind of switch gears, go back to significance tests. So a significance test is statistically significant. We use that specific word, statistically significant, when we get a small p-value, less than 0.05. So statistically significant means we're pretty sure that our results didn't just happen by chance. Like, we're pretty sure the null is not plausible. We're pretty sure we have evidence for our alternative hypothesis. Okay. So for example, we have bottles of orange juice that are supposed to have 16 fluid ounces. Someone suspects the bottles aren't full enough. They take a random sample of 2,000 bottles that contain an average of 15.99 ounces and the standard deviation of 0.2 ounces. Test the hypothesis that the bottles are being filled correctly against the alternative that they are not full enough. So what we want to test, if our population mean mu equals 16 or if mu is less than 16. That's kind of our question, right? That's what we're interested in. Now let's summarize the sample info with the correct symbols. So my sample size equals 2,000. My sample mean equals 15.99 ounces. And my standard deviation for my sample is 0.2 ounces. Let's see, my null hypothesis, that's always an equals, it's always boring. So just like my population mean mu equals 16, and my alternative is my population mean mu is less than 16. Now I need my theory-based p-value. Can I use my theory-based p-value? Well, my sample size is huge. It's much bigger than 30, so I can definitely use a theory-based calculator. So I go to my theory-based. I have to pull up the mean. I put in my sample size of 2,000. I put in my sample mean of 15.99 and my sample standard deviation of, I'm not good at remembering these in my mind, 0.2. So 0.2. Calculate, and I want a test of significance. You have to put in what you're comparing it to. So we're comparing it to 16. Make sure this is a less than. That's what we want. We calculate. My p-value is 0.0127. So 0.0127. So are my results statistically significant? So yes, that is a small p-value, smaller than 0.05. So we have evidence that against the null. The null is not plausible. We have evidence that the population or the long run average is less than 16 ounces. Okay. That's a pretty small p-value. We have quite a bit of evidence. We are quite sure, statistically speaking, that my long run average is less than 16 ounces. It is statistically significant. However, the question is, as a consumer, would you care if you are given 15.99 ounces instead of 16 ounces of orange juice? And maybe you are different than me, but I would say no. Like, I wouldn't care. I couldn't tell the difference. Okay. So this would not matter to me. It is not important. Okay. And this is very important because there's a difference between, do we know something statistically? Like, I am very sure that this average is less than 16 ounces. Okay. Do I care if it's less by 0.01 ounce? No, no one's going to care. That's not actually important. And so in statistics classes, we talk about something called statistical versus practical significance. So significance is not the same thing as importance. So statistical significance means we're pretty sure, statistically speaking, there's a real difference. Like, I went from 16 ounces to 15.99 ounces. Okay, so like I'm fairly sure. When we say sure, like we can make mistakes, but we're sure that our population mean mu is less than 16 ounces. Okay. But practical difference, the difference would actually be important, practically speaking, in the real world. Like, would it actually make a difference to you, to real people? So the difference from 16 to 15.99 ounces does not matter. Okay, so we do have statistical significance. So we're statistically significant, but we are not practically significant because it's not important for our orange juice example. Now, if you have a large sample, even tiny differences like a 0.01 will show up as statistically significant. Like, we can be like, oh yeah, we're sure, but they might not actually be important. So you do have to be careful with huge sample sizes that even the smallest differences will show up as statistically significant. So for another example, a 2013 study of more than 19,000 people showed that those who meet their spouses online are more likely to have high marital satisfaction. They had a p-value less than 0.001 to those who meet offline. The effect was actually tiny, so meeting online barely budged happiness from like 5.48 to 5.64 on a 7-point scale. But why was the p-value so small? So the p-value is small, but that's not a very big difference. So the p-value is so small because the sample size is huge. So statistical significance is not practical significance. Just because you have a really small p-value doesn't mean the difference would actually matter to anyone in the real world. So if the sample size is big enough, even the tiniest difference will be statistically significant, meaning the difference was unlikely to happen by chance. But the scientist, or you as the reader, have to decide if the difference is big enough to actually matter in real life. That's practical significance. But just to know, if your sample size is too small, then even like a huge difference that would matter in the real world won't show up as statistically significant, because the test says, oh, that difference could happen by chance. So it's kind of this balancing act. We don't want a sample size that's too huge, mostly because it's going to be super expensive. But if our sample size is too small, then we can't actually show anything. We can't actually ever find any evidence for any hypotheses if our sample sizes are too small.